Okay, so real ice on melt head in 5, 4, 3, 2, 1, now. There you go. Cool. So now we're melting Antarctic ice.
We are indeed.
Very old ice. The melt rate, so again we need to wait so the melt rate can change.
We are currently working on the Beyond EPICA Oldest Ice project, and this is a major international consortium to drill what we hope is going to be the oldest ever continuous ice core from Antarctica.
Behind Beyond EPICA there are 10 countries. We are supported with a grant of the European Commission for about 11 million euros, but we also mobilize something like other 19 million from national funding, cash and in-kind, to go in the field and to retrieve these ice cores that will reveal us the history of our climate.
Currently, greenhouse gases and sea levels are rising, and although we understand that this is a result of human activity, it's really vital that we understand the natural climate processes, particularly the interactions between our ice sheets, the oceans and the atmosphere, so that we can start to predict what's going to happen in the future.
Beyond EPICA builds on the EPICA project. EPICA stands for the European Project for Ice Coring in Antarctica, which show an iconic record of the climate of the past over the last 800,000 of years. But when we retrieved those results in 2004, we realized that there was a missing gap exactly at the bottom of the core, because we were entering in a extremely important climatic transition, which is called the mid-Pleistocene transition, in which the climate of our planet changed completely the way to operate. We were thrilled about that, and we say, well, we have to find the oldest ice. And that's why we went beyond EPICA.
So the time period that we're really interested in and we're working on right now in the lab is this period between 800,000 years ago and 1.5 million. And it's known as the mid-Pleistocene transition. And during this time, for some reason, as yet unknown, the transition from these shorter glacial cycles to these larger glacial cycles occurred. And what we want to understand is why.
For this project, we needed to drill 2,800 meters of ice from the surface to the bedrock. When we're drilling an ice core, you can only peck out a little bit of ice at a time. You'll lower your drill down into the ice, and then we drill out a few meters of ice and then raise the drill up again. Now, when we're getting towards the end of the project as deep as this one, this can be incredibly slow. If you're lowering the drill 2,700 meters, say, you're near the bottom, that could take an hour and a half just to reach where we got to carry on drilling. Then you'll only drill 4.5 meters before doing that hour and a half journey all the way back up to the surface again. The ice cores are about this diameter, and we've drilled 2.8 kilometers of them, so they take up a lot of space. We filled probably about 2 shipping containers worth just of the ice that we're bringing back to Europe. And moving that much ice is a real challenge. We have to cut it up into meter-long sections to get it into boxes, and then it needs to find its way from our site in the middle of nowhere in Antarctica back to labs all across Europe to do this work. So it was driven overland to a nearby station, flown in a light airplane from there to the coast, where it was put in refrigerated containers to get on a ship, so it could sail all the way back to Europe via New Zealand and then be distributed among the labs, and that took months. After so much hard work in Antarctica, so much difficult work in difficult conditions, by so many people across so many years, it really is a relief to see the ice that BAS is working with here in our labs.
So behind this door here, we have the cold room, so we keep this at -25. And I'll just show you through so you can see Sean is actually working on some sticks in here now. So just a sneak through. So Sean is in there. Say hi, Sean. So Sean is preparing the sticks, which are then going to go onto the melt head. Right now, the labs are really busy. We have the whole team from the UK involved, but we also have a lot of our partners from different labs across Europe. And so it's a very busy place right now. And the teams are working incredibly long hours because once that ice is melting and it's on that hot plate, we are continuously adding more sections to it. And we don't want to stop. We want to be working for as long as possible to keep those instruments running. And so a key part of what we're doing is making sure that everything is linked up in time so that we can link it back exactly on depth on that ice core, which will ultimately turn into an age scale so we know where we are in time going back historically.
So we've also been using this space in the lab, this door, just to keep a record of where we're getting to with the project. So it's a nice place for everyone to keep record of, the milestones we've gone past or the data that we're, comparing to, and yeah, just sort of keep track of everything.
We're going into the freezer, into the -25 freezer, because we've got the best job. Let's go. Okay, right step. So we've been slowly melting away. I think we've got through 1, 2, 3, 4 boxes, and we have 1.5 boxes left.
So each day what we need to do is prepare the cores. So these are the sticks that are 3.5 centimetres by 3.5 centimetres that were cut by our colleagues and collaborators in Germany. But they have been inside a plastic bag, and what we want to do before we put it onto the melt head is clean it. So we carefully clean the outsides to remove any potential particles or fibres that may have been introduced since the drilling process. So this is how we start the day, preparing the sticks, making sure we have enough ready so that we can continuously keep layering up those sticks on top of each other and melt for 10 or 12 hours.
So this is melted enough now that I'm going to swap and put on a new ice core without knocking over all these weights. So you simply detach it. So I'll use this tool to push it beyond the pin. So I've got that loaded up, so I'm going to put this back on the contraption. Slowly turn it towards me. Nice. There we go. You can see the melt head just here. It's a copper-plated melt head. I don't know if the microphone can pick it up, but you can hear it melting on the melt head, and then you can see the outer circumference of the stick going over the side of the gold-coloured plate that's going to waste.
The melt head has a special design in that it has one central hole, but it also has 4 holes around it. And what that means is that as it melts, the outer layers are melted and they go down what we refer to as the waste lines. But the inner line, therefore, never has contact with the laboratory air.
So this campaign is of high complexity, mainly because we are coordinating various groups, and also we are analyzing a precious sample that every drop that we melt is a record that won't come back. We are basically creating story second by second here. And it's also quite complex because our water budget is quite tight. We only have a limited amount of water that we can melt from the inner side of the core, and we have to feed all these instruments, and each of these instruments has a particular demand for water.
My role is to ensure the continuity of this CFA campaign, our continuous flow analysis of the Beyond EPICA Oldest Ice core. And that means I'm continuously keeping an eye on the melt rate, that it's always feeding the entire system steadily at the level that each instrument needs. One reason to do continuous analysis is also that we ensure that the signal is covering the continuity and the gradual nature of transitions that we have in the climate. While when we have discrete samples, we will always have averages of these little snippets, which will maybe create steps within the record that are not real, and it helps us to resolve the more gradual nature of climate.
We haven't actually counted, we probably should, but yeah, we're measuring more than 60 different things in this lab. So through from water isotopes, conductivity, through to all the elements on the mass spectrometer, dust samples, iron, soluble ions. Yeah, we're just collecting so many things from just one stick of ice. So this is a mass spec, so a mass spectrometer, and that's broadly used for collecting elements. So that's like some of the chemical analyses we do. And this one instrument can collect many things all at once, but we're collecting 33 elements. There's another similar instrument next to it, so the OES. That's very similar, it's collecting elements as well, but it's a different type of technique, so it's an optical technique rather than a mass spectrometry technique. All of these things are like jigsaw pieces, you know, they're very small bits of information on their own, but all together, when you put all of these things together, yeah, you create a full jigsaw which has, you know, climate information in it.
So over here we've got the liquid as it's coming through, and then it's going through these various pumps to different instruments. And we're going to follow the line in this direction to this particular instrument, which is measuring stable water isotopes. So the team that are responsible for this are coming from various labs across Europe. And so this week we have Enrico here, who's visiting us from Venice. And so he's going to explain what the isotopes are doing.
So the idea is to measure in an indirect way the temperature of the permeability fast. But obviously we cannot measure directly the temperature from the ice, we cannot obtain this kind of signal. So we need to measure something which is linked to the temperature of the past, and this is called the climate proxy. And in this case we're measuring, as I was saying, the water stable isotopes. We can see the data in live directly, and then every day we're going to save the data inside our backup system. We're going to calibrate them, and so we hopefully obtain a climate record which tell us the changes in the climate of the past.
The next suite of instrumentation, this is part of the line that's looking at dust, so particulate material.
It might sound a bit weird in the beginning, but you can find amazing climatic information in the dust that's in the ice core. So during the ice ages, during the cold times, you've got a really dry planet. Big loads of dust are blown out of all the continents and then deposited in Antarctica. And if it's wetter and warmer, you won't find that much. So you can actually follow those cycles. So what I'm doing here is mostly collecting some discrete samples. We're working under laminar flow, so under clean air, to ensure that there's no extra dust coming in. So we collect samples for Bern and for Milano, and then I'll mostly just stir it a bit so that the dust is everywhere in our sample, and then split the sample so that it can be later analyzed by the two groups for different components. Honestly, it's just really, really, really interesting to work with such a group and such an international team as part of a thesis. That's awesome.
We are continuously analyzing the presence of dust, but also we are analyzing particles that are less concentrated in the melt. In particular, we are taking samples of volcanic ash called tephra, and also phytoplankton called diatoms. They are not so common to find them in ice, but for some reason they end up on top of the ice sheet. So for example, in a liter of melted water from an ice core, you can find about 100 diatoms, compared to, for example, thousands or tens of thousands of particles of random dust. So then you have to be very careful on what you're analyzing, and it's basically like looking for needles in a haystack.
I am the rogue biologist in the ice core team. Mostly I feel really privileged to be on this project because not often do the biologists get a look in. Most of this kind of science and this department is dedicated to climate data and building up the past climate, which is super important. But these are very remote, unique places, so we can find microbes that have unique adaptations or have been able to survive conditions from different times, which is very useful. So if you can see this one, it's the manifold overflow, and it gets a constant drip that goes through the system from the inner lines, which is very important for me because I want water, meltwater that hasn't been contaminated by the outside, specifically humans or equipment, because that stuff is covered in bacteria. I'm going to be taking it and filtering it, and if you can see the filter I have here, this is a very fine black filter that filters at 0.2 microns. So it should collect all of the bacteria, all of the cellular matter that might be deposited in the ice and ice core record, and I'm going to take that, put it, filter it onto these kind of filters, and then stain with fluorescent stains for DNA. And using that, I should be able to tell whether there are any cells with DNA inside the ice core.
One of the cool things is that we're so interdisciplinary in this team, and that we're coming together from different institutions. You get to know people that are working on ice cores, but from a very different angle. For example, we've got colleagues from Heidelberg who have come to us for this campaign to measure the krypton, and that's never been done before as part of our lab, and it's not been done in this way for ice core projects before, so we're learning a lot from each other.
We collect the gas from the ice in order to date the ice in these specific depths. We do the dating with the help of the unstable krypton-81 isotope. It has a half-life of about 230,000 years, so the concentration of the isotope in the gas decreases over time. And with this decreasing concentration, we are then able to determine the ice age, so to say. So the meltwater from the inner channel reaches the debubbler over here, and then on the bottom only water leaves the debubbler and reaches the other systems, as for instance the heavy water isotopes. On the top we have the overflow with all the gas and a little bit of the water to really make sure that no bubbles can reach the other systems. So this is the next bag we will attach, and they are pre-filled with nitrogen so that we don't have any remnant ambient air inside.
One thing I contributed personally to the project is this little squeezer. I not built it, but I designed it. So the measurements of the metal is perfect for squeezing these bags. And we put this thing around and squeeze out the nitrogen through this line. So everything is clean and isn't contaminated with normal air. Yeah, that's the one part I contributed.
So in addition to all of the instruments that you see in this laboratory and some of the samples that are being collected, we also have another line, another tubing that's going over the top of our cold room and into this room in here. So this is a class 100 clean room. And because we're interested in very, very low concentration traces of contaminants or impurities in the ice, we need to keep everything ultra clean. And that's what this lab is for. But it's probably easier to show you through the window the team that are working in there. This is really so that we can ensure that the samples that we're looking at, the samples that we're analysing are staying ultra clean. So we're avoiding any particles from getting into them. And over in the far corner there you can see those lines that started again on that melt head in the cold room being pulled over the top of the ceiling, drawn across by those pumps, and they are again dripping into these various different vials and tubes, because these will then be separated and distributed to different labs around Europe.
Hi, I'm Manon. I'm an analytical chemist in the ice core team here at Bath, and this is the Class 100 clean room. It is where we are currently collecting fractions directly from the melt head, and it's also where we make standards for all of our equipment.
Hello, my name is Azzurra, and I come from Venice, Ca' Foscari, and I'm here in this period to take care of this precious samples. Actually, what we do here is to collect fractions from these tubes, this tiny capillary that will be analyzed in other laboratories, such as, for instance, in Venice. So we will have at the end the continuous analysis from the lab behind, but even the offline analysis of the meltwater that we save now here.
So you might not necessarily think that ice cores and volcanoes necessarily go together as an area of research. You know, they're often on complete opposite ends of the planet to each other. But evidence of volcanic eruptions often ends up in ice cores, either through spikes in the sulfur concentration, which usually comes from a large volcanic eruption, or tiny pieces of volcanic ash, which can miraculously travel from anywhere in the world to the tiny 1 metre drill bit of ice that we take out of the ice sheet in Antarctica. And we're looking for both as part of this project. So out in the outer lab, we're looking for volcanic ash, and in here, these tubes are going to be analysed for sulfur and their isotopes up in St Andrews.
So for this project, I am working on organic contaminant. So the organic compounds are always in the high scores, and what we are doing is to develop a robust method that can detect trace levels of these organic contaminants, organic compounds in the high scores. If we are able to detect these compounds and find some concentration or a significant concentration, we can use that to build a kind of model, which is, so we call it a paleoclimate reconstruction. So it helps us to determine the climate activities in the past, and this data can also be used to model what's going to happen in the future in terms of climate change and climate risk.
It's really exciting being able to see the data as it comes off in real time, so day by day going back further in time and starting to piece together this story of how did the climate change and why. But it won't be until we've really had the time to delve into this and look into it with all the different communities and all the different records to establish the true age scale. That's going to be the key thing here. What time period are we really covering? And then bringing it all together, we hope is going to be some really exciting results. We can see from our data that we're definitely capturing clear climate signals, but what do they really mean in relation to the gas record that's being produced in different laboratories, for example? That's where it's going to start to become really exciting.
Something that was quite special about this project is its international nature. We had colleagues from all over Europe and other parts of the world working together in the field. And we all had our own parts to play. We all came from quite different backgrounds, but we were all able to work together really well to get this job done. And it was really fantastic to be involved in something of that kind of scale with that level of cooperation.
So from the previous EPICA campaign, we learned for the first time what happened with the climate of the past over the last 800,000 years. And that fueled work for the last 2 decades. And now with this project, the Beyond EPICA Oldest Ice project, we are pushing the limits. We are reaching over 1 million years of climate history. And we are pretty sure that this data, the one that we are collecting here live, will fuel what we know about climate in the next decade or so.
This will be an iconic set of data for the next 20 or 30 years for sure. I feel very proud of what we did, because it really is something that we dreamed for a long time. We saw the team growing up around the project, so it was a long process that now we can see the end of the tunnel and we can see that the results are popping up.
These kind of projects in ice core research, it's so vital that we have strong international collaborations and funding. Moving forward, this is going to be a fantastic project that the UK have been able to take a real leadership role in.